Okay, how's everybody today? Great, good, doing well. Okay, we are getting close to the end of the 6 weeks. It is tomorrow. We're going to go ahead and continue. It only should take us, I would say, probably about 5 minutes to wrap up this current lesson here. You got the homework for it. Let's go ahead and have that due Monday. Okay, so the homework over Introduction to Limits, we'll have that due Monday. We'll go ahead and get started with the derivative lesson, the other one you picked up today, in just a little bit. We'll keep going. Remember, next Tuesday and Thursday, we're taking the English STAR exam, so it's going to be a late start day for a lot of folks. 1:35 is when the bell will ring. I will not see you Tuesday. I'll see you on Thursday. So as of right now, it looks like we're going to have this current homework assignment due Monday. We'll have the derivatives homework assignment due Wednesday. The 30 minutes I see you Thursday will be an exit ticket, and then I'll have a quiz for you on Friday. So we are going to go ahead and take quite a few grades next week. Yes, sir.
What time does second period start for Tuesday?
I'd have to take a look, but remind me at the end. I know all the classes start at 1:35, and they're a little different because I don't remember what class they're going to put the announcements in, but they're increased it by 5 minutes. So.
Is this from last week? The order? Because like I've got Tuesday and Wednesday, and pretty sure we already did this.
Yeah, that we're already past.
Okay.
So there's the Introduction to Limits.
Oh, okay.
That's what we're currently. Lucas.
So wait, how do they start for Tuesday, Thursday?
If you're not taking the English exam, just Tuesday and Thursday. Monday, Wednesday, Friday of next week are normal school days. Okay. All right. Anything else? Okay. Excuse me. Well, let's go ahead and wrap up this lesson here, and then we'll go ahead and start getting into derivatives, and you'll see how the limits are going to become important to us. So this last problem, it says a cylindrical vase is placed under a tap of water and is allowed to flow in. Water is allowed to flow into it at a constant rate, and that's the key word there. Okay, a constant rate. Provide a graphical representation of A, the relationship between the volume of the water in the vase and the time for which the water flows into the vase, and B, the relationship between the volume of the water in the vase and the height of the level of the water in the vase. Okay, so let's go ahead and just kind of talk about maybe some units of measurement here. You'll notice I already went ahead and started drawing on the cylinder. You like my water here? You can tell that was water? Exactly. Okay, there we go. So let's go ahead and say that the radius of this is something simple. Let's say the radius is 1. We'll talk about inches. Okay, so 1 inch. All right. Now, you have 3 questions very similar to this one on your homework assignment, but I'm just going to kind of walk you through to kind of get you to visually see how this is happening. I don't think it's necessary on those to go ahead and create tables. I would just kind of reason your way through like you have in past standardized tests. Remember where you have something like snow is falling and then it stops and then it increases or decreases, where you have to create a graph based on, say, the accumulation or something like that. Basically, that's what we're doing here. We're just wanting to give a visual representation, in this case, for A, between the volume of the water and the time. Okay, so let's start out by saying that we're just going to be taking these values in 1-minute increments. So let's say we have 1 minute, 2 minutes, 3 minutes, ... Well, when it comes to the volume, the radius, the height, do we have a formula that can relate all of those for me? What would the volume of a cylinder be? Okay, well, let's start with the base. What kind of base would we have? Okay, so it's a circle, so pi r squared. And then what would I multiply that by? Okay, so pi r squared times the height. Okay, so that's a formula that relates the volume, the radius, and the height. Okay, what we're looking at here. Now, is there any of those that are constant? The radius. Now, because of this, the way that the vase is shaped, the radius is going to be constant no matter how much time has passed or how much water's been put in. So if the radius is 1, well, then the volume is just pi h, right? Because r squared, 1 squared. Okay. Well, for our purposes, let's just go ahead and say that that equals some value, and let's give it a variable. Let's say k. Okay. So let's say the volume is going to be k cubic inches per minute, because that's the unit of measurement that we decided to go with. Okay, you can go with seconds or centimeters. I mean, really, the measurement doesn't matter. Okay, now this is going to represent the change in volume. Okay, well, so let's say in 1 minute, let's say that we get the K cubic inches per minute. Okay, so can anybody tell me what do you think is going to happen at 2 minutes? Knowing that the radius is constant, and more importantly, that the flow of water in is constant. Yeah, it's just going to double. So at 1 minute, if I have K cubic inches, then 2 minutes, I'm going to have 2K cubic inches. 3 minutes would be 3K cubic inches. And then just kind of think about it. If I were to choose a value for K, like let's just say 1. Okay, well then I have 1, 1, 2, 2, 3, 3. So the relationship is just a linear function. Okay. As time increases, the volume of the vase is going to increase. Okay. Does that kind of make sense? Now remember, this problem is dependent on a couple of things. One, the fact that the radius remains the same, okay, for the entire vase, but also more importantly, the water's flowing in at a constant rate. This wouldn't be possible if the water was flowing in at different rates or if we stopped it or anything of that nature. Does that kind of make sense? Okay. So let's do the same thing for B. This was the relationship between the volume of the water in the vase and the height of the level of the water in the vase. Okay, so you'll notice I've got height and the volume here. So let's actually solve for the height. So I want to take a look at this portion right here. We were saying that, at a certain time, we're going to have K cubic inches of water in the vase. So if I solve that for the height, what would I have? Yeah, K over pi inches, right? Okay. Well, if we're going to go ahead and say that at 1 minute I would have K cubic inches of water in the vase, well then at 1 minute, it makes sense I could say K divided by pi inches of height for the vase. Okay. But what kind of relationship do you think is going to happen here under these conditions? What's going to happen at 2 minutes? Would it be similar or different than what's happening with the volume? It would be similar. So what would you expect me to put here for the height at 2 minutes? 2K over pi inches. There you go. 2K over pi inches. Then at 3 minutes, 3K over pi inches. And then that pattern would just continue. So what you're actually going to come to find out is that the relationship we have between the volume and the time, and then we say the relationship between the height and the volume would actually be similar. We're talking about the change in one with respect to the change in the other. So like when we're talking about the first one here, I seriously considered going through this a different way, but how many people would recognize this if I'd use that notation? Does anybody know what that stands for? Bless you. Okay. Okay, this represents a derivative. This is referring to the change in volume with respect to the change in time. Okay, and there's another way you could look at this, but I thought this is probably the better way to go because we haven't really talked about this notation or derivatives yet. Okay, so any questions on that? No. Like I said, I don't think it's necessary for the 3 problems on your assignment to go ahead and run through all that. Just kind of try to visualize it. Like you did way in the past where you had some of those problems. Like let's say, and this is kind of off topic here, but we never get off topic in this class. I thought that'd get more of a reaction. Okay. Let's say, time and distance from home. Okay. Let's say after school, or not, well, let's say you get up in the morning and you're going to go to school. So you get in your car and you start driving at a constant speed. And that's, certain words that you have to hear constant. So if I'm driving at a constant speed, well, what kind of graph would you imagine I start with? Yeah, it's linear. As time increases, I'm driving at a constant speed. But let's say that you go ahead before you go to school. Let's say you pull into Sonic and you go ahead and order a drink or you order some food or something. Okay, well, what's going to happen to the graph for the amount of time that you're at Sonic? There you go. See, your distance from your destination is going to remain the same, okay, for however long you went ahead and spent at that location. And then what's going to happen if, like, you decide, oh my gosh, I'm late, I got to get to school faster? The line's going to be more steep. There you go. Or if you decide, hey, it's such a beautiful day, I'm going to take my time, the line would be less steep. That's kind of what I was getting at. Just kind of reasoning your way through based on the object you have with the water flowing in. Is everybody kind of okay with that? Okay. I don't know what you would call those problems, but everybody remembers doing those at one point or another? Okay. All right. Good. That's what I was referring to. Okay. And then, of course, in that situation, if you're about to go to math class, you want to go really fast, right? Of course. There you go. That's exactly right. You want to get there before you got there. Okay. All right, so if the average rate of change is the slope of the secant line, how do we find the rate of change at a single point on a curve? What we refer to as instantaneous rate of change. Okay, that's what we refer to as a derivative. Okay, to do so, the basic argument revolves around the notion of magnifying near the point where we wish to find the instantaneous rate of change. That is by repeatedly zooming in on a section of the curve. This will give the impression that over a very small section, the curve can be approximated using a straight line. Finding the slope of that straight line will provide us with a very good approximation of the rate of change to the curve. To obtain the exact rate of change at a particular point on the curve, we will then need to use a limit approach. Okay. So we actually kind of alluded to this the other day. Just think about the curve that we were looking at yesterday when we were doing average rate of change. We had some curve like this. We called it F. Well, we can find the average rate of change between 2 points on a secant line, but it's not going to be continuous because it's not a linear function, right? So if I were to choose this point here, some value of x, okay, if I place a tangent line there, the slope of that tangent line, okay, that's what a derivative is going to find you. It's going to find you the slope at that one particular point in time. That's why they're referring to it as instantaneous rate of change. Because if I continue to move around the function, if I choose another value of x here, that point will have a different what? That point will have a different slope. This point right here would have a different slope. It's constantly changing because it's not linear. And that's what a derivative is going to do for you, okay, in a nutshell. There's a lot more to it, but for our purposes, it's going to immediately be able to find the slope at any point on a function that we want, okay, instantaneously, hence instantaneous rate of change. Okay, now before we go ahead and get into the next lesson where we will start using the difference quotient, and I'm going to walk you through that, let's go ahead and practice this real fast. Let's say we have, some kind of function here. And we've got all these limit statements. All right. So we got 7 of these things. Now, let's go ahead and do the first 3 together. So it says the limit as x approaches 3. Now, it says plus. What does that mean? There you go. When you see a positive or a negative as a power, that tells you what direction you're going to approach that value from. So the positive tells me I'm approaching it from the right. The negative tells me I'm approaching it from the left. Now, the limit tells me I would be approaching from both directions. But the limit only exists if I'm approaching the same value of y from both directions. So let's do number 1 together, and then I'll give you a few minutes to go ahead and kind of fill in the rest of them, and then we'll talk about it. Okay, so let's see. As we approach 3 from the right, so 1, 2, 3. Here's 3 right here. So I'm approaching it from the right. So as I get closer and closer, every value of x is going to have a corresponding y value to it. So I get closer, I have this one. I get even closer, I have this guy right here. What would you say is happening as I approach it from the right? It is getting closer to 3, but what's the graph actually doing? The y values are what? The y values are increasing. It almost makes me believe there's what there? There's an asymptote there. Okay, so what if I were to continue to get infinitely close? The values of y would continue to do what? Become infinitely larger. So the limit as x approaches 3 from the right, well, that would be infinity. Remember, it doesn't approach a specific number, but they're just increasing without bound.
So when we're looking for the limit, that's like the y value
Yes, basically what's the y values doing? Mm-hmm. Just think now, this here, what we're doing is we're looking at it visually instead of what we were doing in the lesson. We were looking at the table and looking at it numerically. Okay. Unfortunately, we won't be able to do that here because we don't know what function provided this particular graph. But that's okay. That's why we're practicing. Okay. What about number 1b? The limit as x approaches 3 from the left. Okay, so here's 3, approaching it from the left. Now this one is already much more vertical, so it looks to me like that point there. The closer I get to 3 from the left, what's happening? It's increasing without bound as well. So what would I put? Infinity. Okay. Now, what would you say the limit as x approaches 3 of function f is? I would say infinity. Okay. From both sides, whether the left or the right, the corresponding y values continue to increase without bound. So I can say that limit exists. Remember, the limit only exists if you approach the same y value from both sides as you approach the x. Okay. So let me give you a few minutes to take a look at that. Okay. Number 2, we're looking at -4. Then we're looking at -6. We're looking at infinity. So we're looking at what we call the ends. Okay. And what else do we have? Then we have some true or false statements. Okay. Okay, that's been 2 minutes. You may not be completely done. That's okay. But let's talk about these answers here. 2a, the limit as x approaches -4 from the right. Okay, what should I put? It is -8. Okay. Now, this is where you want to be careful. What is the value of the function when x is -4? Oh, it's something. If I were to take the function and I did input -4, I should get what, Caitlin? I should get a +2. Because, see, that's exactly what I have right there. The solid dot tells me that that would belong to the graph. But when we're talking about the limits, remember the other day we said that the function does not have to be defined at that specific location in order for the limit to exist. So as we approach -4 from the right, see, the y values are getting closer and closer to -8. What happens if I approach it from the left? It's still going to be approaching -8. So now you'll notice from both the right and the left of -4, the function is approaching -8. So what is the limit as x approaches -4? It is -8. See, the left and the right approach the same value, so therefore the limit does exist. How many people got that? Okay, good. Let me go ahead and erase these right here. Okay, well, let's go ahead and take a look at 3a. The limit as x approaches -6 from the right. So I'm approaching -6 from the right. What are the corresponding y values doing? Looks like they're increasing. Looks like they're increased without bounds. So I would say what? Infinity. Okay. Well, what about the limit as x approaches -6 from the left? Okay. That's decreasing without bounds. So this goes to -infinity. Okay. They're getting infinitely smaller. So now, here's my question. 3c, the limit as x approaches -6 does not exist. Well, wait a minute. Why was I able to do that up here for number 1, but not down here? There you go. On number 1, we had infinity on both sides as we approached that +3. But here on both sides of the -6, one was positive, one was negative. They are not approaching the same value, so it does not exist. And I don't really mean to refer to infinity as a value, but just what we wrote down there, our idea. How many people had that right? Okay, good. Now, this is what we refer to on 4a and b as the ends. Okay, what is the function, the graph itself, going to approach as x becomes infinitely larger and x becomes infinitely smaller? Well, it looks like this graph, you could probably infer that there's a vertical asymptote here at -6. There's one right here at +3, but there's also another asymptote where? It's 0. It's the x-axis. There is an asymptote going through there. Okay, so let's take a look. As x goes to infinity, it looks like the graph is doing what? It looks like it is approaching 0. So I'm going to go ahead and say, as we approach infinity, it's approaching 0. Well, what about the limit as x approaches -infinity? Same thing. It's just approaching 0 from below this time. Okay. Now, is anybody kind of confused as to why we would have a horizontal asymptote going through this thing? Because we've always been taught, can the graph and the asymptotes ever intersect? There you go, because here's the idea behind this. What is this right here? That's the origin. That's the one place where both the x and the y axes meet. That's 0, right? So when you're looking at the ends, a problem like this, remember, you're only interested in as x goes to positive or negative infinity. Okay? But the reason we can go ahead and have a horizontal asymptote through here is because 0 isn't infinity. The further we go onto both positive and negative x-axes, okay, the asymptote begins to exist. But it doesn't exist yet because it hasn't reached what we refer to as infinity. Does that kind of make sense? It's always an abstract idea. In pre-calculus, I think it was hard for some people to kind of grasp that idea as well. Any questions about that? Okay. Hey. It would be 0. Okay. And here we're not going to write a single statement because you'll notice what we are approaching, infinity and negative infinity, we're going in 2 different directions, even though they have the same limit. Okay. All right, well, let's take a look at these last ones right here. Number 5, true or false? F of -4 equals the limit as x approaches -4. Okay, well, let's see. We actually talked about this a second ago. What would I get if I plug -4 in the function? I would get 2. Okay, and what do we say the limit as x approaches -4 is? -8. So does 2 equal -8? False. That is false. Okay. What about number 6? Emily, what do you think? True or false? It is true. It is true. Well, let's see. Let's try the first one. The value of the function when x is 1. Okay. So if I look at 1 right here, okay, go straight down, looks to me like it's what? Negative 8. Okay. So negative 8 equals. Well, the limit as x approaches 1 of the function. Well, on both sides, if I approach 1 from the left, if I approach 1 from the right, there you go. You are approaching negative 8 from both sides. Yeah. So negative 8 does equal negative 8. That is true. Okay. How many people got that one right? Okay. Good, good, good. And here's our last one. How about Caroline? What would you say for f of 2 equals the limit as x approaches 2 of f of x? True. It is true. Okay. So what's the value of f of 2? So when x is 2, looks to me like we have that coordinate 2, 0, right? So let's see. The limit as x approaches 2, well, if I approach 2 from the left and 2 from the right, now they're approaching it from different directions, but they are approaching 0. So 0 would equal 0, yes. Okay. How are we doing? What do we think of limits? Okay. All right. Well, we'll see them again. We got some review. I even have a few more graphs like that as we go through into our review session. Okay. So let's switch gears a little bit. Why are limits so important to us? Well, I'm glad you asked. Okay. Let's take a look at derivatives. For a continuous function, y equals f of x, the average rate of change, AROC, of f over a closed interval PQ is basically the slope of the secant line connecting the 2 points P and Q. Okay. Now, we have an example here. It says for the function 3 plus x squared, find the gradient of the secant line joining the points. Let's say the first point is a, f of a, and the other one is a plus h, f of a plus h. So you remember yesterday when I drew out that graph, and h was the horizontal distance between my values of x? Okay. Would you like me to kind of sketch that again, or is everybody kind of okay with this? You want to do it again? Okay. So let's say we have some kind of function. Okay. I'm just going to use the same curve. Let's go ahead and do this one here. So let's say I have this value of x right here. We call this function f. So the corresponding point, okay, the y value here, okay. Oh, they're using a, aren't they? All right, let me go ahead and use a then so it's all consistent. So here a is x. Okay, the variable doesn't matter. So whatever this function does to a in terms of operations, okay, we refer to that as f of a. So we have a, f of a. And then let's say further on down the line, we want a different value of a. But let's say, again, using their variables, they're h units apart. So what's the value of this one? A plus h. Okay. So what I want to do is go straight up to my function. Okay. So to get this value right here, I should be able to take a plus h, plug it into the function, and it results in whatever y value we're going to end up with here. So this would be a plus h, f of a plus h. Okay. And then it goes into taking the slope, the change in y over the change in x. So here we're going from this second point to this first one here, f of a plus h minus f of a over a plus h minus a. But you'll notice what happens in the denominator. The a's are going to cancel, okay, which is what they're getting right here. They just didn't go ahead and simplify out those a's. All right. Well, what we're trying to do is take this particular format, and we're going to go ahead and apply it to the function itself. Okay. So you'll see what they did. We've got 3 plus x squared. Well, for the first point, if I take that value of a and plug it in, well, that's just 3 plus a squared, right? But then here's what always gets a few folks. In the second time around, I want to go ahead and plug in a plus h. Okay. I'm going to simplify that, and then I'm going to expand it. This is what's going to become known as the difference quotient. I'm just going to go ahead and label that for you. This is the difference quotient. Okay. Now, when you simplify, you're going to go ahead and get down to probably something that looks like this. Now, I'm kind of surprised they went ahead and stopped there because you'll notice, what do both numerators share? Yeah, they both share h, right? So I would have taken the time, in fact, I'm going to encourage you to do so, okay, 2ah over h plus h squared over h, and go ahead and simplify as far as you can possibly go. So see, those h's cancel. I've got a pair of h's that cancel. So this ends up being 2a plus h. Okay. Now, this lesson has us looking at this in steps. It wants you to be able to simplify this difference quotient first. When we feel comfortable with that, then we go ahead and take the limit. Taking the limit as h approaches 0 of this function provides you with what we refer to as the derivative. Okay, so give me just a little bit of time. I know it's confusing right now, but hang in there with me. It's all going to connect. Okay, it's going to connect. So let's try a problem. Okay, let me get rid of this right here. Don't need you. Oh, he bounced back. Let me try that again. Technology. All right. So let's see here. For the gradient, find the gradient of the secant line joining points a, f of a plus h, f of a plus h for the function 2 plus 3x squared. What it's telling me to do is apply this function to this right here. F of a plus h minus f of a all over h. That's what it wants me to do. Okay. So I would probably suggest, until people really start to get the idea, in the beginning, why don't we go ahead and just write our information out to the side. Like, for example, f of a. Well, remember, f is your function, no matter what he is. The value of x, we're just calling it a. Well, that means all I want to do is replace every single x with what? Yeah, whatever's in the parentheses is what I'm going to go ahead and substitute in. Like if I wanted to go ahead and find, f of 1, then I would say 2 plus 3 times 1 squared. And then you simplify, right? The only difference is we're using a variable here. It could be anything. So what would that be? 2 plus 3a squared. So 2 plus 3a squared. And see, there's nothing to simplify because I don't know what a is. So we have to stop there. Now I'm going to go to the second part. I want to evaluate the function at a plus h. So f of a plus h. So if I replaced, in this right here, f of a, if I replaced every x with a, and now I want to evaluate f of a plus h, what am I going to replace every x with now? No, a plus h. Okay, see, that's the new input. There you go. So this would be 2 plus 3, but instead of x squared, a plus h squared. See, a plus h just represents a different value of a further along the x-axis. Remember, just like I showed you graphically. Now this we can actually simplify. We can go ahead and expand that, distribute the 3, probably even have a like term that we can combine. So let's take it one step at a time. Okay. What would I get if I squared a plus h? Perfect. Now here's the thing. In case you're not sure where that came from, let me go ahead and write this out. 2 plus 3. Eli said a squared plus 2ah plus h squared. Okay. See, I have 2ah. I'm about to sneeze. Oh, there you go. She gets it now. Let me write that a little better. Okay. 2ah. Okay, because there's 2 of them. He just got it. Okay, there we go. All right. Anyways, back to the math. There's different ways you can do that. If it helps you out, because not everybody does it the same way, if you're able to look at it and expand it, that is fantastic. Okay, but if you have to say a plus h times a plus h, how do we multiply binomials together? What's that acronym we like to use? FOIL. First, outside, inside, last. Would anybody like me to run through that? No? Now, there's also something else that I do. If I'm squaring a binomial, there's a little rhyme. The folks I've taught before, do you guys remember what that rhyme is? Square the left. Well, first, square the left. Square the right. You doubled the middle. Really? You don't remember? You get it right. Okay, there you go.
We didn't even have it on we knew.
There you go. See, I'm a poet and I didn't know it. You want the best? Go to the west. Okay. Okay, so let me show you how this works. So let's say I have a plus h squared. Well, the first term is considered the left term. The second term is considered the right term, so square the left. A times a would be a squared. Square the right, h times h would be h squared. Now here's where some people get a little confused. Double the middle means to multiply the two terms together. So I'm going to multiply a times h, and then I double it. And there you go, there's your expansion. Okay. So again, however you want to go ahead and do it, perfectly fine. Okay. All right, now we're not completely done with this one because what can I do with the 3? I can go ahead and distribute. So this is going to be 2 plus 3a squared plus 6ah. I did 6. I did 6 that time. Okay. Plus 3h squared. Okay. Is everyone okay with what I did? All right. Well, see, now that I've got these two expansions here, there's nothing else to combine. That's as far as I can go, you know, not knowing what h is, not knowing what a is. Well, now take those expressions and plug them into your little formula. That's basically what the difference quotient is. So for this first part right here, where it says f of a plus h, plug in that expression that we just got. So I'm going to say 2 plus 3a squared plus 6ah plus 3h squared. Okay. Now I'm going to subtract, and you'll notice what we're subtracting is f of a. Well, we have that right here. But since I'm subtracting a binomial, I would encourage you put it in parentheses because you're going to have to distribute in order to drop those. So I'm going to go ahead and put parentheses 2 plus 3a squared. And this is all over h. Okay. So now, we just simplify. Let's see here. That would be 2 plus 3a squared plus 6ah plus 3h squared. What? Minus 2 minus 3a squared. And that's all divided by h. Okay. Well, do we notice anything?
You can subtract it and divide it.
Okay, so like 2 minus 2, those are out. 3a squared minus 3a squared, those are out. Okay. And now you'll notice both terms remaining have an h. So can anybody just tell me what it is? So it'd be 6a plus 3h. That's what we're going for right now. Now, we're not quite there. Remember I said we're going to do this in parts. We're going to see this for the first time tomorrow, but this would allow me to find the derivative. Okay, we just have to do one more simple step, and I guarantee it's a simple step. It takes 1 second. That is not an exaggeration. Okay, please tell me we have to, well, we got 203. Depends on what the next one is. Okay, so let's try this one. Okay, find the gradient of the secant line joining 2 points, 1, 1, and 1 plus h squared. Let's skip to C for right now, because I want to go ahead and show you another one that actually has a function. Okay, so for this function right here, I want to apply this guy. F of a plus h minus f of a all over h. What do we call him? That's the difference quotient. We use him to find the derivative. Now, we haven't found it yet. Okay, we got one more extra step. It's real easy. Okay, all right. So now, if I'm going to find the derivative using this formula, there's 2 things I need to do. First, I need to find f of a. Well, what does it want me to do with a? There you go. Every x in my function, I'm going to replace it. So 1 minus x squared would become 1 minus a squared. Now I want to do the same thing for f of a plus h. Okay. So now, how would I do that? There you go. Again, whatever is in parentheses is what's going to be substituted for x. So 1 minus a plus h squared. Now remember, you got to follow your order of operations. So you'd want to expand the square first and then do what? Then distribute. Okay. So we actually just saw this one a moment ago. This would be 1 minus, well, what's a plus h squared? A squared plus 2ah plus h squared equals. Now we just distribute the negative. Is everybody okay with what I'm doing? Okay. So this would be 1 what? Minus a squared minus 2ah minus h squared. And see, I can't go any further than that. I don't have any like terms, nothing. Okay. So now, these two parts that I found, in order to start the formula, I need f of a plus h. Well, I have that right here. So I'm just going to replace f of a plus h with this expression. 1 minus a squared minus 2ah minus h squared. Okay. Now, I need to subtract f of a. Well, f of a is right here. I'm just going to plug that in. So I'm actually subtracting 1 minus a squared. See, it's f of a plus h minus f of a. Is everybody okay with what I'm doing? Okay. And it's all over what? All over h. Okay. Now what? Distribute. So 1 minus a squared minus 2ah minus h squared. That would be minus 1 plus a squared all over h. Okay, so 1 minus 1, negative a squared plus a squared. And there you go. We can get the h out. Sorry. So what would my answer be? Okay, negative 2a minus h. Yeah, this one would still be negative. But ultimately, what's going to happen when we find the derivative, it's going to disappear anyway. So as far as using the formula, how do we feel? Okay. I'll give you another one when we come in tomorrow. We'll go ahead and practice it. And then I'm going to show you how the limit can help me give the derivative. Okay. And we're just out of time. There we go. Perfect.